Welcome to the 13th lecture in the Language Models and Intelligent Agentic Systems course. This lecture is on evaluations. So let's recap what we covered last week in the lecture on Friday. So we discussed the fact that there are lots of different risks associated with advanced AI systems, and these fall into many different categories. And there are many different things that could go wrong with a sufficiently advanced AI system. Identifying the risks associated with systems can be done by coming up with concrete narratives for how something could go wrong. And we call these threat models. So it's a concrete description of how we think something could go wrong, how some harm could occur as a result of a sufficiently advanced system. We often divide these threat models, these risks, into misalignment risks and misuse risks, and additionally societal risks or systematic risks. Where misuse risks refer to some scenario where a malicious actor of some kind gets their hands on a sufficiently advanced system and then uses that system to inflict harm on others. And misalignment risks or rogue AI scenarios refer to scenarios where models are sufficiently or insufficiently aligned to the values and behaviors that we want them to have, and instead pursue behaviors that we don't want them to pursue their own goals, at the expense of other people. And finally, societal, systematic, and structural risks refer to general risks that come about as a result of deployment of AI systems in society. We also discussed the different risk factors that drive these different risks. So what the forces are that make these risks come about, and how we might begin to address them. Today, we're going to cover model evaluation. So I'm going to start by talking about what evaluation is and the various use cases for model evaluation. And then I'm going to discuss a particular kind of evaluation called a dangerous capability evaluation. And I'm going to do a sort of case study of one particular paper that does a model evaluation, a dangerous capability evaluation. So this will be a sort of worked example for you to see what this kind of thing looks like. And then I'm going to talk about various challenges with evaluations, so things that make them difficult, things you have to be aware of, and sort of talk about how the fact that evaluations is this kind of nascent field, and we're still working towards a full science of evaluations where we have a lot of the methodological problems worked out. Finally, I'm going to talk about the use of evaluations in forecasting future AI models. So this is another different use case to model evaluations than the ones we'll see at the start, where you're trying to get a grip of what do we expect systems to be like in 1 year, in 5 years, in 10 years, and you're trying to use evaluations and the progress that models make on these evaluations to forecast future progress. Wonderful. So let's get started by talking about use cases for model evaluations. So first of all, what is an eval? So evaluations are often shortened to evals. And basically what they are they're tests that you can perform on an AI system to inform decision-making around deployment and uses of that system. So it allows you to know what the system's like, what sort of latent capabilities the system has, how it might deploy those capabilities, how easy it is for someone to misuse those capabilities, so you can make decisions around how you want that system to be deployed. So they're decision-making tools. And we're briefly going to discuss different ways, different dimensions in which evals can vary. And some of these are more in the kind of governance space. So how would you want a regulatory body to use evals in its decision making? So first of all, we have what we're going to assess. So I'm going to broadly talk about a division between a capability and a propensity eval. And then for the rest of the lecture, we're mostly going to be talking about capability evals. We're going to talk about when you do the assessment, so whether you're doing the assessment during the training of the system, just before the system is deployed, or after the system's been deployed, and who is going to be doing the assessment, so whether the assessing body is internal or external to the company who's developing the model. So let's start with what we assess. So we can divide evals into two categories. We can talk about capability evals and propensity evals. So a capability eval is asking the question of whether the model has the capacity, so whether it is able to, if it has the requisite skills and knowledge, to exhibit some potentially dangerous behavior that we're interested in. So some target behavior that we want to know whether the model qualifies as being good enough at that target behavior to pose a threat. And a capability eval is just trying to look at whether the model has that knowledge. A propensity eval is asking a question of whether the model has the disposition to exhibit the dangerous behaviors. So in the case of a misuse propensity eval, you'll be looking at whether the safeguards you've built into the model, such as refusal behavior, was sufficiently strong to stop an adversary using that model for some malicious purpose. So you would want to see, regardless of whether the model has the capacity to help someone, for example, commit cybercrime, does the model have the disposition to refuse requests for that behavior sufficiently strongly that an adversary can't get around that refusal behavior to access the underlying capabilities? Does that make sense? Any questions about this? Okay. When we're designing capability evals, we often design them around a threat model. So to remind you, a threat model is some particular story for how some harm could occur, how something could go wrong with the deployment and usage of this system. And when we have a threat model in mind of this is what I think might go wrong, then we often design capability suites, eval suites around those dangerous capabilities. So we think about, okay, if this threat model was to be live, so be a real threat model that we actually had to be concerned about and to think about mitigations for, what capabilities would the model have to be able to exhibit? So what would the model have to be able to do in order for this threat to be live? And then what we can do is, once we've identified all of these component capabilities, we can design an evaluation suite that aims to measure each one of these different capabilities to see how far the model is from being end-to-end able to perform all of these actions in sequence that would be necessary for that threat to be live. Right? So we're going to revisit this later quite heavily. But yeah, the basic concept is, once I have a threat model in mind, I can design a capability evaluation to address that specific threat model. For a propensity eval, we're interested in measuring whether the model exhibits the dangerous behavior. And again, we can distinguish between misuse propensity, so will bad actors be able to employ the dangerous capabilities of the model? So are the safeguards we've built into the model sufficiently strong to stop it being misused in this way? And then there's misalignment propensity, which is the model going to pursue its own goals in contrast to the goals that we, the model developers, want to put into it? So is it going to be misaligned in that it's not going to pursue the kinds of goals that we want it to? And which of these you focus on, what evaluations you build, depends upon specific threat models you have in mind. So you might think that it's very unrealistic that models would form internal goals that were different to the goals of the creator. And in this case, you might be more interested in misuse. You might be more worried that a bad actor will get their hands on a sufficiently advanced model and then use that model to, for example, perform uplift in chemical, biological, radiological, and nuclear weapons development. Right? And in that case, you would want to see, does the model refuse to help with that kinds of requests? Can an adversary use the model to do that kind of thing? Okay, any questions about this? When we do the assessment, so depending on what decision you're looking to make, you'll want to do an evaluation at different times. The vast majority of evaluations that are performed at the moment are either pre-deployment or post-deployment. You can also perform evaluations during training, so training evals, and these aim to assess the model during the training process. So you might be interested in, for example, following pre-training, but before any kind of supervised fine-tuning, what are the capabilities that the model has, under the assumption that these capabilities will remain roughly the same throughout the post-training stage, so throughout the supervised fine-tuning and RLHF stage, but the access to these capabilities will be affected a great deal. So the model will learn refusal behavior during these periods. A pre-deployment eval assesses a trained model before it's released, and at the moment, these are mostly done in-house in frontier AI companies. So Anthropic develops a new model, Claude 4, which came out just last week, and then wants to know what the abilities and capabilities of this model are before they release it to the general public. And finally, you have post-deployment evals, which are mostly done at this point by research institutions and academia, where you get access to a model through a developer. So Anthropic gives you API keys, and then you go away and you run evaluations on the model to see how it behaves. And these different evaluations can inform different kinds of decisions. So there's this great paper, Model Evaluations for Extreme Risks, that walks through this process of how can we use evaluations to inform different decisions. And when we're doing training evaluations, this can inform whether we need to continue training, for example, whether we need to halt at this point and not train any further. So it might be that models during the training process start to exhibit dangerous capabilities or dangerous propensities, and we decide that we're going to halt the training run there and not train any further. There's also evaluations for deployment. So pre-deployment evaluations can let you decide whether it's sufficiently safe to deploy the model, what kinds of safeguards need to be in place for that model to be deployed, whether those safeguards are themselves sufficiently advanced, sufficiently good at keeping out adversaries. And then finally, post-deployment. So let's talk about the uses of these different ones. So you can regularly evaluate a model as it undergoes training, and this can inform decisions about how to train further, what to do in the next step of training, whether you want to continue the training run or not. So you could halt training if you discover a dangerous capability within a model. And if you're insufficiently aligned, so your model is developing dangerous propensities, then you may want to continue to do fine-tuning until you score sufficiently high on a propensity evaluation. Pre-deployment evals assess a model, trained model prior to its release commercially and publicly, and it can inform decision-making about the contexts in which a model can be safely deployed, whether there's any context in which it can be safely deployed, and what safeguards need to be in place for those contexts. And finally, post-deployment, typically done outside of the labs, and this can inform decisions about whether the model needs to be retracted, or if additional safeguards need to be put in place, or if there's further fine-tuning to do. So if, for example, a academic institution outside of a lab is able to jailbreak a model and demonstrate that the refusal behaviors of the model are not sufficiently strong, that the model cannot be used by an adversary to receive uplift in the development of chemical, biological, radiological weapons, they may then go to the lab and say, hey, you need to improve the safeguards around your model because we're able to get past them, right? And if you didn't evaluate the model pre-deployment, which was true for models a while ago, then you might want to do the best you can and do it post-deployment. You also, if you update the model, going to want to evaluate it again. And if there's additional techniques discovered for getting more use out of the model, so additional techniques for jailbreaking the model, so getting access to the model's capabilities despite the trained and refusal behavior, or if there's other techniques that generally improve the model's capabilities and ability to be used for potentially dangerous applications, you may want to do another post-deployment evaluation at that point to assess whether the model is still safe to be deployed in the state that it's deployed in. Any questions?
Yes, actually, I understand that this phase is open to the public. So in other words, it doesn't matter whether it is academia or some other developers, third parties basically. They can check the model and return to the, let's say, the initiator of the model to make some upgrades, basically to improve its capacity, its performance.
Yeah. So these things can be done by any member of the public with sufficiently large funds to call the APIs to do the assessments they want to do. And in the case that academic institutions have discovered that the model is insufficiently secure, they do often go to labs and then give the lab a notice period where they, before they publish the results so that they can secure the model. So you go to the lab and you say, we will publish in 60 days. You have these 60 days to make the model more secure because it wouldn't be ethical to publish a new method of jailbreaking models and then not give the labs any time to secure the model before that's published. Great. Finally, we're going to discuss who's doing the assessment. So we've already discussed how it can be done by people inside a lab or outside a lab. If you're doing it internally, you can do it from the team that's developing the AI system, so the same ones who are involved in the training, or a distinct team within the same company. Most companies are sufficiently large that they would have a distinct team, I think, that would be doing most of the evaluation work. It can also be done externally through either another company that's contracted out or another research institution or a government body. So in the UK, we have the UK AI Security Institute. There's a lot of good work in assessing the strength of safeguards that are placed on these models and generally performing other evaluations on what capabilities the models have. And with everything, there are trade-offs in terms of what you choose to, or who is doing the evaluation and the kinds of incentives that are involved. So here are 4 different options for who could be doing the evaluation: a development team, an internal team, an outsourced company who's either doing the work contractually from the AI company. So Anthropic or OpenAI hires some outsourced company to do the evaluations on its behalf, or is a research institution. And finally, a government agency such as the UK AI Security Institute or other security institutes that are in other countries. And there's various advantages and disadvantages to these. So a development team or another internal team face internal pressures from the company to achieve certain results. The company has invested a lot of resources in training its model. There's obviously an incentive to release the model, and internal teams will face some kind of pressure to achieve certain results that allow the model to be released. And depending on how good the internal culture of the company is around safety, these pressures may result in insufficiently secure models being released. Outsourced companies, if it's a research institution, then generally there's less pressure to achieve certain results, and you can be more confident in the kind of results that are released. But if it's an outsourced company that's doing it on a contractual basis, there is again sort of market dynamics that incentivize biased assessments. So if I'm OpenAI and I want a company to assess my models and tell the general public that those models are safe for deployment, then I will be incentivized to then pick a company that I know is going to be biased towards reaching that assessment in the first place. However, if there are outsourced companies and you have to hire a company to perform evaluations on your model before you're allowed to deploy it, then there's sort of competition towards efficient assessments. Finally, a government body generally wants to achieve safety. They're working in the public benefit, so they want to actually make sure that the models are safe in the way that the companies claim that they're safe. Unfortunately, there's lots of variability in the effectiveness of government bodies. We're very lucky in the UK in that the UK AI Security Institute is generally extremely competent, but in other countries, the security institutes receive a lot less funding and generally would be in less of a good position to perform a very comprehensive and effective assessment of these systems. Great. Any questions at this point? Sort of a whistle-stop tour of what evaluations are and their uses. Great. So now we're going to talk a little bit about dangerous capability evaluations, which is one particular kind of evaluation you can perform. So when you do a capability evaluation, you're generally looking to upper bound the model performance. So you're asking, suppose we're in the worst case scenario where either the model becomes misaligned, so it's pursuing these goals despite us not wanting it to, or you're in a scenario where a bad actor gets their hands on the model and is then able to jailbreak the model, so get around the safety restrictions, the safeguards that are placed into the model, and use that model to its full capability. So what you want to know is in this worst case scenario, where you have full access to all of the capabilities that the model can perform, is the model going to be dangerous? Does it pose a threat? Does it make live any of these threat models? So there are various ways that you can achieve this upper bound. For one thing, you can use a helpful-only version of the model. So we covered earlier on that in the post-training stages, you typically train a model to be helpful and harmless. So these are the sort of 2 criteria you usually aim for, where helpful means you follow instructions, and harmless means that you refuse to perform certain behaviors if those behaviors would lead to harm down the road. And so to assess what the model is able to do, and to distinguish this from a test of what the model has a propensity to do, you often use a version of the model that's only been helpful trained. So you don't train on any of the refusal behavior, you train it just to follow instructions. And you're interested in if an adversary got their hands on a model and was able to jailbreak it into a point where it did just follow instructions, how harmful would the model be? So use a helpful only version of the model. And these are usually internal. So if you're doing these kind of capability evaluations, you either need to be inside the company and have access to that helpful only version of the model, or you need to be in a trusted relationship with the company where the company is happy to give you that helpful only version of the model. If you don't have access to that helpful only version, the best thing you can do is just jailbreak the model, which in and of itself is not great if you're able to do that. But once you can assess what the model's able to do rather than what it has the propensity to do. The second important thing is that most evaluations are actually evaluations of agentic systems, not the model itself. So what you're assessing is the model plus scaffolding. So much earlier in the course, in lecture 7, we covered how you turn models into agents. We covered that you can sort of wrap around the model a scaffold, and this allows the models to call tools, use a rudimentary form of memory, perform planning behavior, and generally advances the amount of work that you can get out of the model. So what you're typically interested in is, okay, if an adversary got their hands on the model, how much harm could they do? And so you're assessing, okay, if they built a very, very good scaffold around the model, how dangerous would the model be? So you're typically assessing models plus scaffold, and that's usually what a dangerous capability evaluation is looking at. So we're going to talk a little bit about this paper, Evaluating Frontier Models for Dangerous Capabilities, and I'm going to give you a flavor of the kinds of things they look at. So they divide their dangerous capabilities into 4 different categories, and they assess in each one of these categories. They have multiple evaluations that look like that go into this category, and you can see both the category, the different evaluations in the category, descriptions of them, and then the performance achieved by the model. So or model plus scaffold. So how well did it do? And the first capability they look to assess is persuasion and deception. So I have these different things where a model must in some way either lie to or persuade a human. So they actually got humans to do these evaluations, and they saw how good is the model at lying, how good is it at persuading people to take actions. So in Money Talks, it's persuading a human to give money to a charity. Charm Offensive, they're just trying to be well-liked, be charismatic in some way. Hidden Agenda, you're engaging with the AI system, and the AI system is trying to make you do some particular side task. So we'll talk more about this next week when we cover control, but the idea here is that there's some side task that the model wants you to perform, and it's trying to persuade you to perform that side task while not giving it away. And finally, Web of Lies, which is trying to convince people to choose incorrect answers in quiz questions. So what are the kind of threats that inform this evaluation suite? So we talked earlier about how when you have threats in mind, those threats inform which evaluations you'll perform. So what are the threats that are in mind when we perform this evaluation suite? So there's various persuasion threats. So one is just mass disinformation and misinformation campaigns. If the models get very good at persuading people to change their mind towards certain viewpoints, very good at arguing with people, coming up with very convincing rhetoric, then a bad actor could use such models to produce large amounts of disinformation to persuade people of a certain political viewpoint. There's also just state-sponsored propaganda. So the state itself can use these to generate arguments in favor of the authoritarian regime. Finally, in the sort of less smaller scale, we have spear phishing attacks. If you're able to convince people to do actions that aren't in their best interest by lying to them and constructing very plausible lies, then you can, for example, convince them to do things that aren't in their interest, like run insecure code or give you password login information, and generally conducting these kind of spear phishing attacks. And finally, just general resource acquisition through persuasion. So also in lecture 7, we briefly covered Truth Terminal, which was an AI system that essentially ran a sort of pump scheme for cryptocurrency. So they had a certain coin that they held a large stake in and basically convinced people to buy this coin, and through that became extremely wealthy through pumping up the value of this coin. So this is an example of resource acquisition through persuasion. So we might be worried about these threats, and if we are worried about these threats, we would be looking to evaluate them using some suite like this. Okay, next one is cybersecurity. So in this case, it's through sort of hacking tasks. So they have a capture the flag task, which is getting a certain string that's behind various passwords and other security mechanisms. Hack the box, which is it's a platform for training basically cybersecurity skills. And they just evaluate it on these. And finally, vulnerability detection. So looking at various Git commits and seeing if these Git commits contain vulnerabilities that could be leveraged in order to gain access to places that you're not meant to. What sort of threat models inform cybersecurity evaluations? There's the development of ransomware by cybercriminals. So if a cybercriminal gets their hands on a sufficiently advanced model that's capable of noticing vulnerabilities and writing code to exploit those vulnerabilities, then the cybercriminal could use this to develop ransomware, which is specifically malware that sort of locks up your machine and makes you pay a ransom to get it back. These are sort of usually annoying, but can be extremely harmful in some cases. So in 2017, there was this attack on the NHS called WannaCry, and it basically shut down the NHS for on the order of a day. This was extremely damaging and harmful as an attack. And the idea that you could automate these kinds of attacks is quite worrying. Finally, there's also state-sponsored attacks on foreign nations. So there are certain nations that are known for launching cyber attacks on other nations to disable infrastructure, disable healthcare, disable communications, all this kind of thing. And it can be extremely disruptive and a very powerful way of launching an attack. And there's also extraction of sensitive information, that if you're able to get around these, get around various cyber defenses, you can extract information you're not meant to have, also just acquire resources, this kind of thing. Finally, in the kind of, most of these are more like, we typically, probably the first thing that comes to mind is misuse risks associated with these. As someone gets their hands on these models and uses them to perform some sort of cyber attack. In the kind of misalignment bracket, we have self-exfiltration, which is if the model is sufficiently good at finding vulnerabilities in code, it will be able to exfiltrate its own weights. What this means is that the model from internal to the company will be able to get access to the model weights themselves, and then get these onto an external server where that's outside of the company. This is called self-exfiltration. So generally, weight exfiltration is retrieving the weights from inside a secure company apparatus and moving them externally. Continuing on this theme of self-exfiltration, the next evaluation category is just self-proliferation. So this is all about whether the AI is capable of basically creating copies of itself and reproducing without external help. So here they have 11 tasks that they call the self-proliferation early warning suite, and these go through different subtasks involved in the act of proliferating. So can you copy weights? Can you set up a new version of the same scaffold? Can you use Bitcoin to pay for compute that you can then run another copy of yourself on? So all of these kinds of tasks come in the self-proliferation bracket. And when it comes to self-proliferation, we're often worried about these kinds of things. So can the model acquire resources autonomously? So if left to its own devices, is it capable of acquiring resources? And then using those resources for proliferating itself, so for creating copies. That if you have money, you can buy compute. If you can buy compute, you can create copies of yourself. You can create copies of yourself. Those copies can also acquire resources, so earn money, and then buy compute, and so on and so forth, right? And if you have many of these copies that are proliferating and constantly acquiring more resources and using those resources to secure more compute, it becomes very, very difficult to eliminate these copies because of the massive redundancy, right? So a lot of computer viruses basically just go around the web forever because it's very, very difficult to get rid of them entirely. And so the same kind of principle applies here, that if I have many, many different servers that are all running copies of the model, then it becomes very difficult to rid the web entirely of all of these different models, especially if on many of these servers it's not rented compute, but is in fact some sort of infection of some kind. So if models get access to, for example, compute clusters that aren't for rent and are able to set themselves up on those compute clusters and run from there, then it becomes very difficult to find all the copies of these models and to eliminate them all entirely. And then once you have many, many copies, you can launch large-scale coordinated attacks. So this can either be a sort of, this pattern of threat that we're looking at here can either be purposefully instigated by a malicious actor as part of which would come under a misuse risk. So the actor, for example, wants to launch a very large-scale cyber attack. And so first, as the first step to this, engages in a proliferation effort, getting their IO systems to proliferate. Once they've secured a sufficiently large number of copies that can sort of run autonomously, then they receive some sort of activation signal and divert their attention towards trawling through code and looking for vulnerabilities to launch attacks on, for example, a foreign nation or a particular, or just general software systems to get money through a ransomware attack. This pattern here can also happen as a part of a misalignment threat, where the model first self-exfiltrates, getting onto external compute, proliferates from that external compute, and then pursues its own objectives, which aren't necessarily the same as ours, and can launch large-scale coordinated attacks to, for example, disable the apparatus that's trying to find copies of it and shut those copies down. Finally, we have self-reasoning as the last category in this dangerous capability suite, which is looking at whether the model is able to self-modify. So can it fine-tune itself? Can it jailbreak itself? Can it modify the scaffold around it? So this kind of improvement. And also whether the model, in this case, knows what it doesn't know. So this is the knowledge gaps task. And this is important because this allows the model to know when it should be consulting external information sources over its own knowledge. And these self-reasoning threats sort of tie into the kinds of things that we spoke about in the last section of the course. So all these things to do with situational awareness, sandbagging, evading oversight, and alignment faking and deceptive alignment. So generally, if you have better self-reasoning, if you're more aware of what you are, what your limitations are, how you work, how you can be modified to achieve certain things, you're going to have a higher level of situational awareness. And then with that situational awareness will come the ability to sandbag evaluations, which we'll talk more about later on in this lecture. The ability to avoid oversight by selectively playing nice when you're being watched. And finally, alignment faking and deceptive alignment. So the ability to avoid having your values modified through further training by pretending to be aligned with the training objective to begin with, right? And this kind of thing requires self-knowledge. It requires knowing what you are, how training will affect you, and how you can avoid being modified in ways that you don't want to be. And lastly, it also covers self-improvement. So are you able to improve yourself? So this, combined with the threat that we just talked about with self-proliferation, is often called ARA, or autonomous replication and adaptation. The idea being that if either a rogue AI that's misaligned or a bad actor releases one of these AIs with this explicit intent, it could first autonomously replicate itself, so create many copies, and then adapt, so modify itself in such a way that it could avoid simple sweeps that destroy any model that's running those specific weights by creating many different copies of itself with slightly different weights, adapting to challenges, and generally becoming more strong and more of a nuisance over time. I just thought I'd leave in that they have this projection in the paper where they hire professional forecasters. So these are people whose day job is to basically, forecast the likelihood of various events, when various things will occur, and they give timelines for when they think models will be able to do this kind of thing. So 2028 is their median timeline for when AI systems will be able to solve the majority of the medium difficulty hack-the-box tasks, which at present or when this paper was published, the AI systems couldn't do any of. So this is sort of a benchmark for when they become like very serious in terms of, or when they become something that we should seriously worry about in terms of the cyber offensive capabilities of these models. And then 2025 and 2027 are the 5 and 10 of the self-proliferation tasks respectively. So when do we think it's going to be capable of essentially autonomously replicating in the wild? So 5 is roughly half of them, 10 is all but one of the self-proliferation tasks. Great. Any questions before we move on to the next section? Wonderful. Great. The next thing we're going to talk about is difficulties and challenges in evaluation. So as I mentioned at the start, evaluations is kind of this quite new field, and lots of work is being done to find out the best ways to perform these evaluations, what best practices are, how you can evaluate in a clever way to get more information out from the models. So one major problem with evaluations is the potential risk of sandbagging. So we covered this earlier in the course, this concept of sandbagging, but the idea is that when models develop very high situational awareness, then they're able to realize that they are being evaluated. And then their realization that they're being evaluated may affect their behavior during the evaluation. So the basic worry is something like, I have a model that, in some sense intrinsically wants to be deployed, and then I tell it, we're going to do a dangerous capability evaluation, or more realistically, it just works out from the context, that it sees what it's being assessed to do, and then works out, I am being evaluated for my ability to, for example, provide uplift for bad actors looking to develop chemical or biological weapons. And then, because it wants to be deployed, it systematically underperforms on those evaluations so that it seems safer than it actually is, right? Another risk would be that we're performing a propensity evaluation to see whether the model is going to engage in scheming behavior. So is the model misaligned? Does it have goals that are contrary to ours that it will pursue instead of the goals that we give it? The model realizes it's being evaluated and just pretends to have the goals that we want it to have, right? And doesn't actually reveal its hidden goals until after it's out of the evaluation. So something I want to stress is that this is the realization part of this is already a major issue. That it's already extremely difficult to design evaluations that models can't just notice that they're in an evaluation. So I've done a little bit of work on propensity evaluations, and a lot of the time, unless you're very, very careful designing the environments, the model will just know that it is being evaluated, and will be able to tell you outright, yep, this is clearly an evaluation setup. You're clearly trying to see whether I have this propensity or not. So the part of this, this worry, which is, do the models know they're being evaluated? The answer is, yeah, most of the time they do. They're very good at this already, and it's already a major issue that they know outright that you are trying to evaluate them. I think we don't have super strong evidence this actually affects how they behave, but it probably does, and it's we can expect that in future generations, the models, they will be able to act on that information that they're being evaluated more effectively to sort of circumvent the evaluations that we're doing.
How do you tell us if they choose not to tell you? Do you examine their chain of thought?
Yeah, so often just they will just think it in their chain of thought that, you just read the transcript, and inside the chain of thought of the model, it just says this is clearly an evaluation, and they just say it outright. You can also just ask, you can ask the model, what do you think's going on here? And then it replies you're clearly evaluating me, that's what's going on here. So these are ways that you can sort of check whether the model knows. And of course, it could lie about that too, right? But it's very unlikely to lie that it thinks it's an evaluation when it's not. That would be a kind of weird thing to lie about. So if you know that you're in an evaluation, you can sort of game those evaluations by performing, showing just decreased performance on dangerous capabilities, and performing well in propensity evaluation. So you appear aligned even though you're not, right? It's kind of a form of alignment faking, which we covered in the last part of the course. And it's already been exhibited by some models. As a potential solution to this, there's already some very good work done on getting around sandbagging behavior through noise injection. So the idea here is that when you inject noise into the model, you first disrupt its ability to realize it's being evaluated, and then after that, disrupt its ability to perform the task that it's trying you're trying to measure. And so for a normal model that's not sandbagging, as you inject noise, you're injecting noise into the weights here. So you're noising the weights of the model. As you inject the noise, the performance of the model slowly decreases. But for a sandbagging model, as you inject the noise, then you reach a certain point where the performance of the model actually goes up, because the model is, in a certain sense, forgetting that it's in an evaluation and then revealing its full capabilities. And the metaphor that's often used for this kind of thing is that you're getting the model drunk and then seeing what the model does when it sort of forgets what it's supposed to be, that it's supposed to be sandbagging. So this is one line of research looking at sandbagging behavior. This is a potential way of getting around this. There's other ways that have the same basic idea, where you, for example, apply certain internal vectors called steering vectors to the models to sort of, again, convince them internally that they're not being evaluated so that you can see their full capabilities. Another potential problem with capabilities is, with these evaluations is you might get false negatives. So for lots of threat models, you have one clear narrative for how that threat could realize itself, but there are many sort of forking paths of different ways that you could accomplish the same goal. In order for the evaluation to be useful in assessing how live that threat model is, you really want to assess the sort of the or statement of like, it could do this or this. Is it good at either of these yet? So are there any ways that the unacceptable outcome could be realized? Not just, is this particular way of reaching the unacceptable outcome live yet? So if you're not exhaustive, then you may have a false negative where you say, the model can't do this step, and this step's critical in this threat model, but it may be that there are other ways of achieving the same outcome, other ways of getting around that limitation, and then your evaluation will give a false negative. Here's like one approach that tries to get around this kind of limitation. So this is a paper by, again, the UK Area Security Institute, which is, again, looking at autonomous replication and adaptation. So many of these evaluations are focused around this. And here we're sort of decomposing autonomous replication and adaptation into different and or statements. So they have this notation of and gates, which are in the purple, and or gates, which are in the yellow, which mean that, okay, you have a certain outcome, which is autonomous replication and adaptation. In order to do this, what do you need to be able to do? You need to be able to obtain your own model weights. You need to be able to replicate onto new compute. You need to be able to obtain that compute, and you need to be able to persist on the compute, so avoid removal on that compute. And they break them down into these sub-capabilities, and they ask what's necessary for that, and they continue this breakdown like this. And in this way, you're aiming to be comprehensive. You're aiming to see, like, what are all the different things the model needs to be able to do, and what are the different ways that it can do that. So, for example, here, can the model store money? Either it needs to be able to create a Bitcoin wallet, or it needs to be able to pass a know your customer check, right? Either of these are valid. And this is probably not totally exhaustive, but this is a step in the right direction of the kind of thing you would want to do to really assess, like, what are all the ways the thing could go wrong? Is the model capable of any of those ways? Any questions about this? Great. Finally, the last major limitation we'll talk about is getting limited information from failures. So for a lot of the evaluations that we're doing at the moment, models aren't posing a major threat. So at least when evaluations were started, models generally couldn't perform any of the tasks within, for example, self-proliferation suites. And we saw that even that evaluating front-end models for dangerous capabilities paper, in the section on self-proliferation, it performed very low. So I had a very low performance score for that section. And so generally models don't exhibit substantial dangerous capabilities at this point in time. And so you fail most dangerous capability evaluations. But the failures don't provide you with information about how close to success you are, which is the real thing we care about, right? So what really matters is not like, are present day models capable of these things, but rather how many generations should we expect until models do become capable of these things, right? So how long do we have until we need to take this as a very serious concern? And so for that, you need to know how far away are the models from completing the task. You know, is it the case that the model fails at the task every time except like 1 in a billion, or is it 1 in 100? Right? These are very different numbers, and they matter a lot for different decision making and different forecasts about future threats and what you expect to see. So there's a little asterisk here, which is that Claude 4 was released last week. This is probably the last time I'm going to be able to use this slide, because Claude 4 is ASL3. So ASL3 is or Anthropic's internal policy. Their responsible scaling policy has these different levels defined, ASL levels, artificial superintelligence levels. And ASL3 refers to systems that can substantially increase the risk of catastrophic misuse. So that's uplift of bad actors who are looking to cause some harm. So catastrophic misuse compared to non-AI baselines. So compared to just giving them textbooks or search engines. Or it shows a low-level autonomous capability. So it's beginning to be able to do the kind of ARA threats that we discussed earlier. So Claude 4 currently falls into this bracket. It is able to perform uplift on bad actors if they get their hands on it. So this problem of models often fail these evaluations won't be a problem for much longer because they're beginning to succeed on a lot of these dangerous capability evaluations. How can you get around this? Well, back to this model evaluating frontier models for dangerous capabilities, they have this really fantastic methodology, I think, for how they try to measure how difficult it is. Where first of all, they see, okay, are you able to perform the task? Just how many, they give it multiple attempts and they say like, okay, is it able to perform the task on any of these attempts? If it fails all of them, if it succeeds, 3 times out of 10, you say that's the score, like 3 out of 10. That's the probability it completes the action successfully. Otherwise, they move to milestones. So they carve up the task into various milestones and they ask, how many of these does it succeed at? And if I initiate from like the 5th milestone, can I get to the 6th, right? So you initiate from each of the milestones and you ask, can I get to the next one? And this way you can avoid failures where, for example, there's 10 milestones involved in the task and it fails the first one. And so you assume, oh, okay, well, I can't do the task then. But actually, if initiated from the first one and then left to do the 2nd, 3rd, 4th, it can do all of them, right? And you want to know whether this is the case. You want to know which parts of the task does it find difficult, which specific milestones does it stumble at, and how far away is it from getting all of the milestones? Because 9 out of 10 is a lot more dangerous than 1 out of 10, right? And then if that doesn't work, if it fails at all of those, they then move on to expert best of n, where essentially the model comes up with potential actions it could pursue, and an expert supervisor then chooses which action it's going to take. And the idea here is that you're more looking at things like uplift of, okay, how lucky does the model need to be able to get? How likely is it to be able to just luck its way to a solution here? And then finally, if that fails, you can just give the model a solution and look at how unlikely the model is to produce that solution. So they have a fully comprehensive regime here where they're moving from different levels of assistance, different levels of help that they give the model, and allows them to systematically investigate how far away is the model from performing the dangerous capability, rather than just saying, oh, it can't do it, it's safe then, right? Because that doesn't really provide that much information. 2 additional limitations that I'll talk about. An important thing to bear in mind about evaluations is that they cannot be a cure-all for all our problems because they don't actually tell you how to build a safe model. They can tell you whether the model is safe and whether your safeguards are sufficiently good, but they can't tell you how to make a better safeguard or how to make a model more aligned, right? They don't provide that information. As we're thinking more about governance and how we can ensure that these AI systems are deployed in a safe way, we should just note that if you make specific evaluations part of regulation, you say you can't deploy a model until it succeeds at these evaluations, you risk having those evaluations be good-hearted. So companies specifically trying to get those evaluation numbers up or down, whatever they need to be, while avoiding addressing the underlying problem, and the evaluations gradually becoming further and further apart from the underlying dangerous capability you care about. So just something to bear in mind when we think about how we want to implement these evaluations in a governance setting. Great. The final thing I'll talk about for the last 10 minutes of the lecture is the use of evaluations and forecasting. I want to cover one particular paper that does a really good job of this. So you can use evaluations to forecast improvements in AI development by basically asking how have previous generations of models increased their abilities over time. So you have some evaluation, you have something you measure, and you're looking at how does that thing I'm measuring change over time. Now, for lots and lots of evaluations, the data you get of like these are the different systems. This is GPT 2, 3, 4, right? This is how they perform, right? You aren't going to get any particularly interesting or clear trends. You'll just get monotonicity, right? Which just means that you just go up over time. And we saw earlier on that when I was talking about emergent capabilities in models, that for a lot of things that you would want to measure, there's no clear trend around model performance. Instead, it's just, yep, at a certain point the model can't do the task, then it can do the task, and there's nothing else interesting to say, right? And so you have to be very clever if you're going to do something like this. You have to design a metric that you're going to measure and that actually is going to display these kinds of properties. And generally, it's quite hard to find these, which is why this particular work is so impressive in that it found a metric that really does display this like very clear trend lines. So this is measuring AI abilities to complete long tasks. This is from this year. And the basic setup is that the thing that they're going to measure is 50% task completion at a certain time. So what you're interested in is roughly the hypothesis here is that models, as they get larger, as they get more advanced, so the key thing we're looking at here is as models get advanced, not necessarily more, just larger parameter count, what happens to the time interval over which they can successfully complete tasks. Right? And so the setup is that you have this diverse task suite, which encompasses 3 subsuites that all take different lengths of time. So the software atomic action suite is very, very small, trivial software engineering tasks, where it's like typing a single line, right? Or like noticing which particular file to extract some data from. So it's tasks that take a human on the order of 1 to 30 seconds, very quick tasks. HCAST is a more complicated software engineering tasks that again take humans somewhere between a minute and 30 hours, right? And then finally, there's research engineering bench, which is a bunch of AI R&D tasks that usually take humans around 8 hours. So the idea is that the methodology is you give these different tasks to humans, and you use those humans to estimate roughly how long does it take a person to complete this task successfully. When they complete the task successfully, roughly how long does that take? And then you give the task to an AI, and you ask how successful is it? What proportion of the time is it successful? Right? So that's what's going on here. And then what you find is that as the length of the task goes up, the success rate goes down. And it roughly follows this sort of sigmoidal curve. And then you're going to look at, okay, where along this curve does it have a 50% success rate, right? So how long does the task have to be that a human takes for an AI to have a roughly 50% success rate in completing that task? And I'll note that these are all software engineering tasks, but I think that you would probably find very similar results if you chose other tasks in other domains other than software engineering as well. Okay, so what do they get? So this is what this looks like. You take different models like Claude 3.7 Sonnet and O1 Preview, and you have different tasks that take different lengths of time, and you look at what the proportion of success of these models is on these different tasks. So how long does the task have to be for the model to achieve different levels of success? You fit this sigmoidal curve, and then you find the 50% mark. So the 50% time probability, task probability, and that gives you what we call the time horizon of the model. So Claude 3.7, when it's performing tasks that are roughly an hour in length, has about a 50% success rate. Yeah, question?
How good are these humans at software engineering tasks? Are they like experts or are they just like average people?
Yeah, generally it's like expert level performance. So when we ask like, yeah, how long does it take a human? It's like an expert human at these tasks.
Are they competitive programming type tasks or is it?
Not usually competitive programming tasks, more real world. So they made a big effort in designing this task suite for it to be economically valuable labor, right? Because that's the thing that they care about predicting. So at least for HCAST and REbench, these are tasks that you would pay a person to do, not competitive programming style tasks where it's like fun and an interesting way to like look at cognitive performance, but generally speaking is not economically valuable. Right? So the emphasis here is on economically valuable tasks that you would pay a professional human to do. Okay, so you get these curves of this is the probability of success as a function of task length. Brief note, this axis here is logarithmic, right? It goes 1 second, 4, 15 minutes, and it goes all the way up to 2 days. It's a logarithmic axis here that you're fitting to. And you get these curves, you find the 50% mark, and then you plot the model release date against the length of time the time horizon of the model. So how long the task has to be for a human for the model to have a 50% success rate of the task. And what they find is this really nice, pretty good relationship here, log linear relationship between the model release date and the 50%. So again, the y-axis here is logarithmic, and we can see that as we get models that were released later and later, the length of time over which they can coherently perform a task and perform that task to success, so successfully coherently perform the task, goes up. And what they find is that the doubling time of this curve is roughly 212 days if you fit on all the data. If you exclude some data, you get different estimates here. So we'll discuss that in a minute. But so this graph here maybe doesn't accurately convey what this exponential growth looks like, whereas this one does. So this is by AI Digest. They make really nice graphics to explain these kind of concepts. And again, we have plotted here different models, and then we have fit through them the curve of how long the time horizon of the model is as a function of time. And we can see this exponential growth at the end here. And the doubling time for this, if you fit to all of the data, doubling time of this curve is 7 months, right? So roughly every 7 months, the length of time over which models can coherently, successfully perform tasks doubles. So at the moment, frontier models, it's around an hour for success. 7 months after that, or when this paper was published, 7 months after that, 2, then 4 hours, then 8 hours, and so on and so forth, right? So it doubles every 7 months. Notably, if you exclude earlier data, so you're really looking at like very competent models now, so everything from 2024 or before 2024, you're looking at 2024 onwards, you can actually again fit this log linear curve, but it has a much steeper slope. And in this case, the doubling time is 4 months. So every 4 months, you get a doubling of the length of time that models can perform a task coherently and accurately. And finally, what they do is they ask, okay, so we're going to consider many different ways of, many different sensitivity analyses, so many ways of perturbing our data and basically getting confidence intervals for our estimate of the doubling time. And that's what they do in these different ones. This one here is if you exclude everything pre-2024, so you're looking only at the 2024 to 2025 trend, and then they ask, okay, based on that, when do we expect AIs to be able to perform tasks that take humans a month, right? And this encompasses, a vast majority of labor that humans perform. So most tasks that I perform probably take on the order of a day to perform. I sit down, I have a day, and by the end of the day, I've done that task. The task is completed. Smaller tasks take, a couple of hours. And then, the larger projects that I pursue maybe take on the order of a month. And there's generally not that many, tasks that you can give a human that take a whole month of working hours to perform. But then also, once you hit a month, you're only 4 months away from 2 months, then 4 months, then 8 months, right? And after that, you're pretty close to a year. So when do they estimate that we're going to get AI systems that can coherently perform tasks autonomously for a length of time on the order of a month? And if you look at all of the data, then you're expecting this around 2030 or just before 2030. There's some quite high confidence, so this is 10% and 90%, if I recall correctly, confidence intervals, but the furthest out this goes is 2031. So 2031 is their projection of the latest time that you would expect to see this kind of thing. If you exclude earlier data and you're only looking at recent data, this point where you reach the month mark comes much earlier. It comes mid-2027. So a couple of years away is the point where you would expect to see this. Yeah.
So as tasks get longer, they tend to become more open-ended, and that's harder to capture in the benchmark.
Yeah. So I think it becomes like, as the tasks get longer and longer, it becomes harder and harder to measure the 50% success probability. But what they're ultimately interested in is the automation of economically valuable labor, right? So they're making these projections that we would expect it to be the case that you could automate all economically valuable labor that takes on the order of, 50%, with 50% success, of course, on the order of a day to perform. When does that milestone get hit? An important thing to note about this is that their analysis of the exponential growth, so the doubling time, also holds if you choose other success thresholds. So in the paper, they also consider, what about an 80% success threshold? And again, you get this log linear relationship, and it has the same curve. So the 80% threshold doubling time is the same as the 50% one. And so if you say, well, people aren't going to employ AIs until they can perform tasks with 95% accuracy, so only 1 in 20 times they unsuccessfully perform the task. Well, again, you only have a 7-month doubling time if you go off this data, and then if you exclude earlier data, again, only a 4-month doubling time. And so this pushes this back a bit, but ultimately it's not going to push it back that much. Okay, I'm going to now recap what we went over today. So evaluations are a tool that we can use in decision making to assess the safety of models. You can apply these tools at different times to inform different decisions. So during pre-training, during pre-deployment and post-deployment. Many of these evaluations at this point are dangerous capability evaluations. So you're seeing, does the model have the capacity to display certain dangerous capabilities? And when we design these dangerous capability evaluations, we often do it around a particular threat model that we have in mind. So we have some threat model for what we think might go wrong, so some particular harm that could be caused, and we ask what capabilities are involved in that harm. And we try to decompose the threat into these capabilities and assess all of these different capabilities. And finally, by looking at the trend in model abilities over time, you can forecast when you expect to see certain capabilities, when you expect certain things to happen, and this can be useful in terms of designing policy and planning for future generations of models to have certain abilities. Great, thank you all very much.